Okay, there was some students in the class making fun because I always start like hello guys, and I say okay, I'm not gonna start hello guys. Sup homies? Today I'm going to solve a problem centroid by integrals, and the problem that I want to solve for you, the first one is kind of a straightforward, and it's a parabola delimited by the two axes here, and I have the parabola y equal x squared. So the first thing that we have to remember is the definition of center of gravity, centroid for this case. It's going to be the integral of x dA divided by the integral of dA. And y bar, or ycg, whatever you want to call it, is the integral of y dA divided by the integral of dA. So if we solve these equations for this part, or for this problem, the first thing that you have to do is decide what you're going to do. And there are two ways of doing this. For not in every single case work, but in the cases that work, I like you to do it in this way. So first thing, if I'm going to do this one, I said I'm going to measure x in this direction, x, and then my differential of area is going to be this one, perpendicular to that x. And of course the centroid of that differential of area is going to be at the center there. So basically, if this is my differential of area over here, and if this is x, this distance, this small distance is the x, and this differential of area is going to be equal to this distance from here to here. I'm going to call that distance, I don't know, h multiplied by dx. But that h is going to be changing because, you know, if this is my differential of area, I was explaining this to one student the other day, and I say, just imagine that this is extensible and adjustable, and these are the limits. So this differential of area is going to change from this value here up to this value here, meaning at this point the differential of area is going to be defined by this height, and this is the x all the time. But at this point it's going to be defined by this height, and so on. At this point it's going to be defined by this height. And that height is h, and h is variable. But if you can see, that h is varying between this point and this point. And this point is not a point, basically, it's a line. It's a horizontal line with equation is y equal 1. So if I say that this is y1 and this is y2, then basically my h is going to be defined all the time as y1 minus y2. And check it out. For this point, y1 is 1 and y2 is going to be 0. So the total height is 1, which is correct. And at this point here, for example, y1 is 1, but y2 is also 1, and the height is 0. So yes, it's defined by these two lines perfectly. What is y1 though? y1 is 1. And what is y2? y2 is x squared. So it's going to be 1 minus x squared. That's going to be my h. And my differential of area for any case is going to be, or for this case that we are working, is going to be that h, which is 1 minus x squared, multiplied by the x. That's the differential of area. I can solve integrals separately, or I can solve integrals at the same time. Let's just solve them independently. So if I want to calculate then my area is going to be the integral of dA, which is going to be equal to the integral of this, 1 minus x squared dx, and this is going to be defined between what and what? Well, this differential of area is running the whole section from this point up to this point, from this point up to this point, from this point, meaning from this point up to this point, and this is the point 0, 1, and this is the point 1, 1, but I'm running it in the x direction, so it's going to be from 0 to 1 in the x direction. So basically this is the integral of this is going to be x minus x to the third divided by 3, evaluated between 0 and 1. And when you put here 1 is going to be basically 1 minus 1/3, because this is 0 minus 0 is 0. So it's going to be 1 minus 1/3, and this is going to be equal to 2/3. That's my first value. That's my integral of dA. Now I'm going to solve the top integral, and the top integral is the integral of x dA. The integral of x dA is equal to the integral of x multiplied by dA, and dA is this equation that we calculated before here. So it's going to be x times 1 minus x squared dx. From 0 to 1 also, because I'm measuring in the same direction. So when you do that, what you get is, this is x dx, meaning x squared divided by 2, and this is x to the third. So when I solve it, it's going to be x to the third plus 1, x to the fourth, divided by 4, between 0 and 1. And when you do the evaluation of the integral, this is going to be 1/2 here, minus 1/4. So 1/2 minus 1/4, meaning this is equal to 1/4. I don't have any unit, that's why I'm not putting units. So this is assumed to be just units. When I have to calculate my x bar, remember, the integral of x dA divided by the integral of dA, while the integral of x dA is this value here, 1/4, divided by the integral of dA, which is 2/3. This is equal to 3/8. So x bar equal 3/8. And this should be, of course, in units, whatever units you have there. Now for y bar, there are two ways of doing it. I told you to start thinking in this way if you can do it. So let's try to follow this way of thinking. This is the equation that I have to apply. So I measure y in this direction, and my dA is going to be this one then. This is going to be my dA. Of course, this distance is going to be dy, and this shape is changing from this value up to this value, meaning from 0 to 1 in the y direction. So the integral of dA, I don't have to do it again because I already did it. The area is the area. It doesn't matter in what way I measure it, in what way I try to define it. But this part, the top integral, then I'm going to solve that as the integral of y dA. And my dA, my new dA, if I use this one, is going to be defined as this distance. Similarly, this value, if this is y2, this is going to be x2 here. So x2 or x is equal to y to the 1/2, because I'm just solving for this x. So basically this differential of area, if I say that this part is, I don't know, b, this length, that b is going to be the value of x at this point, which is y to the 1/2, minus the value of x defined by this line, but this line is x equals 0. That's the line that defines this vertical line here. So minus 0, or just 1 to the 1/2. So my differential of area then is going to be that distance that I call b, which is y to the 1/2, multiplied by this distance, which is called dy. That's my dA if I use the new dA. Then when I do this integral of y dA, integral of y dA is going to be the integral of y multiplied by this, y to the 1/2 times dy, from, remember I'm measuring in this direction y, so from 0 to 1 in y. So basically this integral is going to be, this is y to the integral of y to the 3/2 dy from 0 to 1. So basically this is 2/5 times y to the 5/2 from 0 to 1. So when I do the evaluation, I get 2/5. Now if I apply my equation for y bar, y bar is going to be equal to the integral of y dA divided by the integral of dA, and the integral, this one is the one that we calculated, 2/5, and I calculated before my area right here, which is the integral of dA, 2/3, and then this and this cancel out. That means that y bar, this and this cancel out, and this goes up and this goes down, is equal to 3/5. So then you have your x bar, and then you have your y bar. There is another way of doing this problem, and I'm going to start introducing it right now. Let's say that I don't want to change that way of looking at the problem. And the first time that I solved this problem, I said, let me see if I can find an extra page here. I'm looking for an extra page with the same. There you go, here. Okay. If I decide to keep the same differential of area that I used for the same one, remember for the first equation, which is this one, we said, okay, the first part we said I measure x and this is my differential of area, and I define this differential of area as 1 minus x squared dx. That's what we said before. 1 minus x squared times dx. But let's say that now I want to use the same differential of area and apply this equation. And this equation is y bar equal the integral of y dA divided by the integral of dA, which I already know the integral of dA from before. And remember, the integral for dA is equal to the area, and that's equal to 2/3 because we calculated that before. So my problem is still solving this top part. Now, what happens when we work in this way, and if you're measuring x in this way, this is a differential. This is really small. So whatever distance I measure from here to here is going to go up to the centroid of that shape, because it's just a line. The centroid is located at the same point. Now, if I said, wait a second, I'm going to use now y dA, that means that I have to measure from here to the centroid of this line. But the centroid of this line is going to be exactly at the center of this rectangle. And the center of that rectangle is given by, if we said that before this was h, then now it's going to be h divided by 2. H divided by 2. So the center of this rectangle is going to be h divided by 2. That's the centroid, but it's going to be measured from the curve itself. Okay? But let's say that we are here now, and I want to use the same differential. Well, the centroid of this is going to be right here. But I have to measure it from this axis up to that point. So this centroid, actually, if this is my y for my y dA, I'm going to call it like wiggly y, like that. So if this is my distance that I have to measure from here, that distance is formed by two parts. The first part here, which is x squared, and the second part here, which is basically that h, and the h that we calculated before, it was 1 minus x squared. We calculated that from before, right? For calculating the dA. That h divided by 2 is going to be this part. You see that? So then if I'm going to do it like that, and I'm going to use the same differential of area, there's no problem with that. But I have to be really sure that my distance is going to be this, x squared plus h divided by 2. So my distance, my wiggly y, is going to be h half plus x squared. Or in other words, it's going to be 1/2 plus 1/2 x squared. Or it's going to be 1/2 of 1 plus x squared. That's going to be my wiggly y. and then I can solve with that for the same one. Of course, if I do that, my integration limits are still going to be in x from 0 to 1. So if we do that from that part, then this is going to be y dA, and this y, this is not a square, this is like a wiggly here to indicate this to the centroid of the vertical differential of area. So this part is going to, from 0 to 1, and this part is going to be this times dA, and my dA that I calculated before was 1 minus x squared dx. From 0 to 1. If you do this, this is going to be 1/2 integral 0 to 1. This is a product of a sum by its difference, so it's going to be 1 minus x to the 4th dx, or it's the same thing as saying this is 1/2 the integral of 1 squared minus 1 squared, I mean x. This is the 1/2 x minus x to the 5th divided by 5. This is already doing the integration of this. X to the 5th divided by 5 from 0 to 1. When you do that, then you have 1/2 that multiplies 1 minus 1/5, and this is equal to 5/5. This is 4/5, 4/5, 4/10, 4/10. This is going to be this part. And then remember, if this is just the integral of y dA, then I have to divide that by my area, which is equal to, we calculated before as 2/3. 2/3. And then this goes up, this and this cancel out. This is 2, right? And this is 1/5 actually. This is 3/5, which is the same value that we got before when we did in this way. Now, why do we have to do it like that, or why do I have to do it like that? I don't know. Sometimes it's a matter of preferences, and sometimes it's not. In this problem, in this particular problem, I could perfectly have done it just changing my x and y and my differential of x and my differential of y. But in the next problem that I'm going to show you, you don't have that choice. There's only the possibility of doing it in that way. So I hope that you enjoyed this problem. Go back, try to understand this new part because it's a new concept that I'm introducing to you. And if you can't, for now, just try. And if you can't and it's possible, then do it like that. Because I know this is more straightforward for you to do it. Okay, I hope you enjoyed, and I see you in the next video lecture. Thank you.